Good afternoon. In this video, we are going to talk about proposition 12 from book 1, okay? So this proposition is pretty similar to the previous one, proposition 11. It declares that given a straight line and a point not on this straight line, we are able to construct another straight line which is perpendicular to the given one that is going through the given point, okay? So for example, we are given this straight line L and a random point B not on the straight line L, then we can make a straight line perpendicular to L and through P, okay? So let's start this proposition. So first of all, let's randomly pick up a point on the other side of L. Let's assume it is point Q, okay? So let us review the postulate 3. If we are given a center point and a specific distance, then we are able to describe a circle. So let's assume P is the center and PQ is the distance, then we can describe this circle. Sorry, I forgot this step. Before that, we should join the straight line PQ. Because of postulate 1, we can construct such straight line, and then we can use this distance, okay? So let's use this distance and this center to construct a circle. Okay? And let's assume this circle is intersecting with the straight line at 2 points, let's say A and B respectively. And using postulate 1 again, we can join straight line PA and another straight line PB. Great. And please recall proposition 10. Given a finite straight line, we are able to bisect it. Okay? So let us bisect this straight line AB and assume we bisect it at point C. Okay? And in the next step, let's use postulate 1 again to connect point C and point P. Okay, CP. So CP is the straight line we are looking for, which is perpendicular to L and it is through P. Okay, let's give it a proof. So please recall definition 15, the definition of a circle. In a circle, all radius are equal. So we have PA equals to PB because they are radius of the same circle. PA equals to PB, right? And then we know that AC is equal to BC because AB is bisected from the point C, right? AC is equal to BC. And please note that PC is the side shared by these two triangles. So PC is equal to PC. And combining them together and using proposition 8, side, 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 we know that this triangle and this triangle, they are equal, which means this angle and this angle are equal. So we have angle PCA is equal to angle PCB. And pay attention to definition 10. If two straight lines meet with each other and two adjacent angles are equal, then these two straight lines are perpendicular to each other, right? This is the definition of perpendicular. So we know that PC is perpendicular to L. And this concludes our proof. But I would like to say the proof that provided by Euclid in this proposition is a little bit controversial because he had never mentioned that this circle can intersect this line by 2 points. So let's assume that he assumes that if we pick up a random point Q on the other side of the L, we are able to, then the circle is always intersecting with a line with 2 points. This is true, but it is not proved or postulated. For example, if we describe the circle too small like this, then the intersecting points will be 0. If it is exactly this big, then the intersecting point will be 1. In this situation, the line L is, to be honest, it is tangent to the circle, and the intersecting points will be 1 point. I think the relationship between a straight line and a circle will be discussed in next few books, but at least until proposition 12 in book 1, it is never proved or never postulated. Okay? So I think this is the end of the video, and in the next one we are going to talk about proposition 13. Thanks for watching. Have a good day.